Hi, in this video I wanted to show how I trained a policy for this robot that I designed on Onshape, and the policy is trained so that the robot walks like this. So this is how we would expect a robot like this to walk. Now the problem is, normally if you train a policy with a simple reward function, then it will learn how to do something like this. Very cool, but not very practical. The method I'm going to use is described in this paper, Design and Control of Bipedal Robotic Character, written by Disney research team. And you might have seen this video before, but the model is trained to follow a specific set of animation. So the animation is first generated, and then that animation is put on the robot. So the policy is learning how to mimic basic animation. Now this paper itself is inspired by this other paper called Deep Mimic, and it also describes the same approach. So you have a reference motion, and you ask the simulated policy to follow the joint trajectory and the joint velocities of the reference motion. So by doing that, you can teach it to do various things, not only just walking around, but also, well, getting up in this case like this. Okay, so I'm going to explain the main idea behind those two papers very briefly. In a typical reinforcement learning, we have the observation, current observation, which includes the robot's current state and various other sensor data. And then this is put into the policy, and the policy generates the next action. This next action is taken by the, well, in this case, the simulation, which, well, simulates the robot, and it steps in time to generate the next state and the reward that was obtained during that time step. So this next state is taken and then put into the observation, and then we just keep repeating the loop until the policy is trained. So what's new in this case is for each, so we have a basic animation, which in this example, let's say, has 30 frames or 30 data points. The data points are the target, the joint positions of the robot that we want to make the robot follow. So at time equal to 0, then we tell the observation, or the observation gets the value of time equal to 0, and that observation follows the normal procedure, and then we get the reward function in that time step. Now the reward function then takes the target joint positions from the animation, and we calculate the current error between target joint position and the current joint positions of the robot. So the idea is, when the policy sees the current time, then it needs to output a set of target joint values that match the animation, and in that way we can force the robot to learn how to move like the basic animation. So as we step through in time, then every time we update the current time value and update the target joint position, and then we reward or penalize the policy until we have a very good trained policy like this. And this training, this loop continues on until we finish the animation, and then we loop back around and we just keep going and going until we have a nicely trained policy. So here is my robot model, and I've generated a animation. So when we put the animation on the robot, it looks something like this. And I wanted to first explain how I make the animation for the robot like this. So here's the side view of the robot, and the idea behind the robot motion animation is this leg. Let's use the red color like this. Let's increase the size of the brush. Okay. So this leg is moving in this manner. The leg is moving backwards, and then at some point it will go up and then it will go loop around back again. And this leg is doing exactly the same. We'll move around, come around, and this is the touching point, and then it will move backwards like this. So by generating these trajectory for each feet, we can force the robot to walk like the animation here. So that's all that's happening here. This leg is moving straight, and then we follow a semicircle up like this, and this is doing exactly the same motion, but it's offset by about 15, well, half of the number of frames of the animation like this. So generating this animation is very simple. So all I'm doing is I'm deciding that I want 30 points for my animation, and so the X and Z values are just sampled from a circle or cosines and sines, but with a different weight value. So, we can see here that so this will generate an ellipsoid because it doesn't have the same radius value, but we can set the Z values that are below 0 to be, well, to 0. So we only want the upper half of the animation. So it looks like, let's try see what that looks like. Generate path. There we go. So here is my animation defining positions of the feet. So the leg positions are supposed to follow this trajectory like this. So the next step is the robot has 4 feet. This is the front left, front right, rear right, and rear left. And I'm offsetting each leg a little bit from one another. So it's not exactly a 50-50 split, but this looks more natural to me. So one foot is offset by -0.5, or this is the number of frames, and this one is, well, the opposite leg, which is a little bit ahead or behind in legs. So again, I'm just taking the generated X and Z values. The Y value doesn't move, so it's all zeros, and I'm simply rolling this trajectory path by the offset values, and I just stack it up and output it as a trajectory path like this. So now we have the target feet position for all 4 legs, but these are leg positions and not joint angles. What we want are the joint angles that make the robot feet go to these points itself. So to do this, I'm using two packages. This one is called URDF. This is the only up-to-date URDF Python viewer that I could find. So all it does is imports a URDF file, and we can see the image like this. The main thing that we need to use is this package here, which is called Pinocchio, and this is a inverse and forward kinematics solver. So I can use the position of the feet to solve for the joint angles that make the robot go to that point. The code is a little bit involved, but if you look through the documentation, then you can find out how to do inverse kinematics. But basically, once we process the inverse kinematics, then we get this kind of animation. And this animation is we know the feet position, but what's output from this program is the joint angles of the robot that make the robot follow this joint path or the leg path. So the inverse kinematics outputs a file called joint trajectory, and if we look at what's inside it, and this is what's really necessary for Isaac policy training. Here we have the joint trajectories, and each joint trajectory is named by, well, in this case, these names are from a real spider, but essentially these are names of motors or joints on the robot. So tarsus FL means the front left shoulder joint of the spider or the motor name. And if we look inside each value, so for example tarsus front left, then we see here that there are 30 values that represent the animation for this motor name. For example, at time equal to 0, this motor should have this value, and at time equal to, well, the last frame, then this motor should have this joint rotation value. Okay, so now let's get to the training part. First step is to export the robot from OnShape into URD file. And I've done, in my last video, I explained how I do this process, so I hope you've seen that video. So once the model is imported into, exported as a URD file, I've generated, or I've set the joint limits inside the URDF file itself. So let's, for example, take a look at the tarsus. So this joint has been limited to minus 40 radians, 0.4 radians to 1.2 radians. This joint has been manually set to be within these joint limits. So I can only go up to this point or up to this point inside the URD file. So the joint limits are set inside the URD file. Let's see if we can find any such limits. Okay, so here, for example, this is the tarsus front left, and I've put a maximum effort of 40 newtons. This will be ignored, I think, by IsaacLab. I don't remember. So this is the lower bound, and this is the upper bound. And by manually setting this for each joint, I can fix the limit the joint rotations for the robot itself. So for policy training, I'm going to use IsaacSim, IsaacLab's and reinforcement learning example inside the available environments. So if we click on it, we can see how the robot is set up. This is the manager-based reinforcement flow, and here we have the set of observations that the policy sees, and here we have the reward terms. So as I explained before, we need to input the current time of the animation into the observation, and we also need to input the corresponding target joint position into the reward function calculation here. So given that the example already has all of these code, I'm only going to focus on the 2 additional new tasks. Okay, so in your reinforcement or the manager-based workflow, you will see the MDP section here, or markup decision process. If you don't have it, just copy it from the environment or the available environment section in IsaacLab. So first, I'm going to calculate the motion phase observation. So this is basically the current time of the animation here. So the animation, to calculate the phase of the animation, we need to first decide the how fast the animation is playing in terms of frames per second. Up to now, I have only discussed the frames as corresponding points in some arbitrary time, but here we will have to decide on what the FPS is. This is the number of frames. So in our example, we have 30 frames, and so to get the phase, I get the simulation current time from the MDP here, and this is has a length of a number of environments. Then I multiply it by the animation f frames per second to get the current of the frame ID of, well, the animation. So if the simulation time is progressed much more than well, once in this case, well, second, and that means we have to wrap. Well, if it's more than the number of frames, then we have to wrap. So here is the wrapping done, and then we output simply the time of, well, the phase of the motion. So for example, this value having a value of, let's say, 20 means for that environment we are at animation frame 20. So by doing this observation term, which we include in the motion phase observation, then we can tell the policy what our current environment's current animation time step is. Yeah, I should also mention that I updated a few values. So here is the animation FPS. I have 30 frames of animation, and I'm going to play it at FPS of 36. So if I play it slowly, so if I set this value to 15, then the animation plays over a 2-second interval. Whereas if I play it at 45, then it plays at, well, is it 0.5 or 0.75 seconds here. So by changing this value here, I can make the robot move faster or slower. I've also updated the damping and stiffness values. These were decided by just running many simulations until I found a few values that work. And the robot has 12 motors or 12 joints, and I've limited the maximum effort and the velocity of the robot. So with these settings and the extra observation input to the observation of the robot, well, all that's left is to calculate the new reward function based on the target joint position. So the next task is to calculate the reward term for each environment, which all can be at different time step. So it has to be calculated for each environment with a target set of joint positions here. In IsaacSim or in IsaacLab, or I guess it's in IsaacSim, if you want to add an extra term for well, in this case reward, then you have to take a manager term base, or you have to inherit from this. And in the initializer, you can set up a few variables that you like. So in this case, I am importing the joint trajectory pickle file. Then I'm opening it here. Then for each joint name, I'm converting that into a torch tensor. So this has a data of 12 joints by 30 frames, and each frame is the joint angle that we need to track. So when this term, I guess I should show here. So in the rewards term, I'm using very simple rewards, fewer than the actual ant reward terms. The first one is the progress term. So all it does is move towards a point which is really far away, in 1 kilometer in the x direction. This is the alive term, which is very common. So all we want it to do is stay alive. This is the upright term. So I want the robot to have the z direction, or z direction of the robot also aligned with the z direction of the world. And finally, this is the joint trajectory follow reward term, and this is the most important reward term for following the animation. And in fact, this is not actually a reward term, this is a penalty term, because we have the weight set to -1. And in terms of termination, we have just the normal timeout, but we also have illegal contact termination. So if anything any of these body parts touch the ground, then it's that environment is terminated. And these are all just everything that's not the tip of the legs. So going back to the rewards term, so every time this reward term is called, this calculation takes place. So here we get the sampling current time of that environment. Now I haven't vectorized this yet, but I hope this is a little bit more easier to understand what's happening. So each robot has 12 joints, and each joint has a curve that we need to follow, which is the joint trajectory. So for each joint name, first we have the number of frames here. Then we get the current frame ID. So this is actually exactly the same as the observation term. We get the frame ID. Then we get the, here is the rapid frame ID. And we get the left and the right frames, the closest left and right. So this is not in integers, this is a floating point number. So we get the left and the right frames. And then we get the weight for the left and right frames. Progress between the two left and right frames, and then we simply linearly interpolate between those 2 points. Okay, so these are the joint targets. So what's happening here is the environment is not stepping in equal increments. It can be in any point on this line here. So for example, if it's right here in the middle, or about 75%, then what we want is to take the joint target in this at this step and this next step, and then linearly interpolate between these 2 points. And so that's what's happening here. And so the next is to get the joint position. So this is the current position of that joint, and the reward term is simply the L2 reward here, which is the current position of the joint and the target position of that joint, and then we square it up. We just add that into our reward. So what happens is, if these two are exactly the same, then this reward term will be 0, and if they are different, then this has a positive value, and this reward term will be, large. So by putting in the -1 as the weight, we are penalizing it for having non-zero values, basically. And so for each joint and for each environment, so this is not vectorized for each joint, but it is vectorized for each environment, and we get the total reward for that robot. Okay, and that's pretty much it. It doesn't change very much from the ant example, and we can just simply run the program and see how the training progresses. So here's the script that I use for training. I'm using RSLRL. This is the template task name. I'm using 512 environments in headless mode, and I am outputting videos during training so I can check its progress. So I've stopped the training in about 10 minutes later, or about 10 minutes later. Here is what the training videos look like. So at step 0, you can see it has very random outputs. Step 2000, step 4000, already we can see it's trying to mimic the joint angles. Step 6000, getting much more confident. Step 8000, we're pretty much there. I mean, it's walking towards the target point. So around 10,000, not much has changed. Only took about 10 minutes to train this, and the main idea is that with very few reward terms, we can actually train it by just giving it a base animation to track, and the robot model will learn how to output good joint trajectories while also following the other overturns. Okay, that's it for this video. I hope you learned something, and in the next video I'm going to be training a humanoid robot to walk. Okay, thank you very much.